Okay, continuing on from the last one where we went over isoelectric focusing and plotting, we're going to continue our separation techniques and look at SDS pages. This is a big one, okay, definitely a big one, and one of the more complicated ones for sure. Separation techniques in general and other lab techniques are very high yield, so all this stuff we need to know very, very well. SDS page stands for sodium dodecyl sulfate page, which page is just polyacrylonitrile gel electrophoresis. Those we need to know. They will use those terms in the context of a passage or a question. We need to be able to recognize that. Okay, so sodium dodecyl sulfate. What is that? That is a detergent. They'll use that term as well. We need to know that it is a detergent. Okay, what does that detergent do? It denatures proteins. Okay, so sodium dodecyl sulfate, SDS page, is going to be used for proteins. And the detergent, like I said, is used for denaturation. Okay, so we have a before SDS and after SDS. Clearly, the globular form denatured into, like a linear form. It lost all of its. Any protein will lose its quaternary, tertiary, and secondary structure. It'll just be down to its primary structure. The reason for that is because it can break all intermolecular bonds. It cannot break any covalent bonds. Okay. And the whole point of SDS page, the reason why we want to break it down that way, SDS page is used to measure proteins based on size only. Okay, we just want to see the size differences in a protein, so we use SDS page. Something that helps me kind of just remember what this is used for. Instead of SDS, I just think about it as size discrimination. Size discrimination, and I don't think about that last S. But anyways, if that helps you to think about it, awesome. Okay, so the SDS is not going to break any covalent bonds, which is why the primary structure is still intact. Okay, and we know based on the last video that two big things will determine the migration rate of a protein, and that's size and also charge. Okay, so something else that happens during SDS page, as you can see here, the whole protein has a negative charge. Okay, we want to put a uniform charge on these proteins so that charge has nothing to do with migration of the protein. We want to take out all confounding variables and just look at the size. Okay, so you could say, I guess technically you could put positive or make it neutral, or do negative charge, but since we're using a standard electrolytic cell, we're going towards the anode, which is positive. So we're going to put a uniform negative charge on there. Okay, so it gets a little trickier here because that would be standard SDS page, and now we get these terms non-reducing and reducing. Okay, so this term, they need to tell us if an SDS is reducing or non-reducing. If they don't say anything, okay, if they just say it's an SDS page in a question or a passage, the assumption is that it's non-reducing. Okay, it's under non-reducing conditions. Okay, sometimes they might give us a question and show us a gel, and we need to figure out if it's non-reducing or reducing. Okay, but if they don't say anything, then it's just non-reducing. If they say reducing, then it's reducing. Okay, so we need to be able to detect that. So now what the heck is the difference between reducing and non-reducing? Okay, so I said that the detergent does not, it destroys the intermolecular bonds, but it does not destroy covalent bonds. The peptide bonds are not the only covalent bonds. Okay, disulfide bonds. Those are covalent bonds that make things a little tricky here for us. Okay, so those are going to, hold on to quaternary structure. I know I said quaternary, tertiary, secondary structure. All get denatured but you get the point. All the intermolecular bonds get denatured. The covalent bonds stay, and since disulfide is a covalent bond, that stays as well. Okay, the thing that cleaves disulfide bonds is reduction. Okay, so a disulfide bond gets cleaved via reduction. If we are in non-reducing conditions, okay, if we're in non-reducing conditions, the disulfide bond is still there. The disulfide bond is intact. Okay, under non-reducing conditions. Under reducing conditions, the whole purpose of the reducing conditions is to destroy, is to break the disulfide bonds. Okay, so the disulfide on this gel on the right, I can't spell, disulfide is broken. Okay. A couple videos ago, we talked about how proteins can have multiple subunits if they have any quaternary structure. Those subunits are held together by disulfide bonds. Okay, so we have here a protein made up of two subunits, a 75 kilodalton subunit and a 25 kilodalton subunit. Okay, and the thing that they're being held together with, that they're showing in the middle here, is the disulfide bond. Okay, so that 4' structure is still intact. Okay, which means when we run it through the STS page, the size that is going to be shown is 100. Okay, so if we come over, it's 100 because obviously 75 plus 25 is 100. They're still together, so it's going to be treated like one big protein. Okay, however, once we get to the reducing conditions, the disulfide bond is now broken. Okay, so this dimer, I know it's a dimer because it's got two subunits. This dimer is going to be broken apart into its individual monomers of 75 and 25. Okay, so because of the reducing conditions, the disulfide bridge got broken, and now we can see two blots instead of one. Okay, sometimes, and I know I talked about heterodimers and homodimers, so it gets even trickier. Okay, sometimes we'll have a homodimer. Okay, in this case, okay, they're giving us a heterodimer. Heterodimer, I know it's a heterodimer because the subunits are different sizes. All heterodimers have subunits of different sizes. Okay, but if they gave us, let's say instead of 75 and 25, they give us a 50 and a 50. Okay, and a 50 and a 50 on the left. Okay, we know 50 plus 50 still equals 100. Okay, so that's going to look the same on the left side in the non-reducing conditions. That is going to be the same. Okay, but now the homodimer on the right STS page under reducing conditions, it's 50 and 50. Okay, so each subunit, okay, sometimes they might do it in different wells where you'll have one there, and you can see that they're separated. Okay, so that's, easy to detect when you see two bands. Okay, but most of the time, they won't do that. Most of the time, it's going to be really difficult to interpret. And let's not look at these other ones, just look at the black one. It's going to be a little different to interpret because we only see one line there. We only see one line for the protein, which can be super, super confusing because we know it's under reducing conditions. Okay, so if we didn't have the prior information that the subunits were both the same size, we would have to make that inference. Okay, we'd have to make the inference that, oh, okay, in order for only one band to be showing on the gel, they must be the same exact size. Okay, so that's only possible to show that 50 band if the protein was a homodimer. Okay, because we know that if it's a heterodimer, we're going to see two bands. And something that they do to help represent that if it's that it's a homodimer, sometimes they'll make the band a little bit thicker. Now, I exaggerated it there, and I made it like mega thick. But on the exam, they might make it a little bit thicker. So just be aware of that. If you're dealing with any STS pages and you notice that one band is a little thicker, it might be that there are two bands on top of each other.